All right, so we got the circular motion practice. Starting off with number 1, we got riding a Ferris wheel, radius of 30 feet, wheel is turning counterclockwise at a rate of 1 revolution every 10 seconds. And assume the lowest point of the Ferris wheel is 10 feet off the ground. Draw a pretty picture. All right, so here's the ground, and here is the Ferris wheel. It is rotating counterclockwise, so let's put some arrows here to kind of signify what's going on. I know that it's 10 feet above the ground. Okay, so this distance right here is 10, and it has a radius of 30, so that's going to be 30. And I think that's part A, good to go. Next, we want to figure out the angular speed of this thing. So if it's doing 1 rev every 10 seconds, then we need to turn this into radians per second, or radians per time unit. Doesn't really matter if it's seconds, but so I'm going to do times 2 pi radians every 1 revolution. So this thing, if I simplify, is going pi 5 rads per second. And this is going to end up being the W, or omega, that we use in our equation later on. So part C says that we want to model the path here, and we want to assume that we're starting right here at this point, okay? So in order for us to start at this point and go that way, we have to try to think about some things. So we need to know what the x equation is and what the y equation is. So if we want to start here, that's at the rightmost point. So that's an x value that's at a maximum. So I know x is going to be my cosine graph, starting at a maximum, so positive cosine graph. And if we need to go up, then our y value needs to be positive sine, so that we start in the middle of the circle, so at 0 in terms of like the circle above and below the center of the circle, and we need to go up, so positive. So when I write these equations, I'm going to have x equals the radius, so 30, positive cosine, the speed, pi over 5, t inside, okay? And then I'm just going to center this in the x direction as though this is 0, 0 right there, so I'm not going to add anything because the center point is going to have an x value of 0. Y is going to be 30 for its radius, sine pi over 5, t. This one will be plus 40, so 10 plus 30 in order to get to the center. And then, of course, we always have our t is greater than or equal to 0. Next one is we just want to figure out where someone's position is when the ride stops after 22 seconds. So the way we show our work for this is we just do x 22 and y 22, and we just plug those into the calculator. And it is important, we are in radian mode here. Okay, because we're doing pi over 5, that's in radians. If we had put maybe 36 degrees there, then we could have gotten away with leaving our calculator in degrees, but we didn't. So, let's see. I think I get both of these numbers here, so 9.27 and 68.53. And next we want to know what is the distance. Okay, so I'm going to erase the top part, leave myself a bunch of empty room over here for the calculator to hopefully show up. So we have one person is getting on the ride, okay? I shouldn't have erased my picture. If they get on the ride right here, that's at 30, 40. So that's where one of the people is getting on the ride. And then the other person is at this point way down here, the 9.27, 68.53. So I just need to do the distance formula between those two equations. So just basically type it all into the calculator, and I get 35.2671 feet. So that is the distance between them at that moment in time. So 22 seconds into the ride, when it stops, the first person is at an x value of 9 and a y value of 68, so that's like somewhere up here, and the actual distance between them, straight line distance, is 35 feet. Woo! Man, this board is dirty. I think it's just a eraser. Those of you watching the uncut version, enjoy. Question 2. parametric equations, trace a circle, radius of 2. We're again going to assume that they start at 0, 0. Okay, so we have a circle that's centered at 0, 0 with a radius of 2 in all directions. So the first one says we're going to start at 0, 2. That's at the top. So I just like to draw just that part and then put a little point where I'm starting in terms of the circle, and we're going counterclockwise, which is that way. So I need to figure out what's going on with x and y. We always look at the starting point. That is a maximum y value, so y is going to be the cosine graph, and that means x will be the sine graph, but we're going negative in the negative x direction, so it's going to be a negative sine graph. So for part A, it's going to be x equals -2, negative because it's negative sine, 2 because that's the radius, sine t. We don't put anything else in there because they didn't tell us if it has a speed. The center is 0, 0, so we don't add anything else. And this will be 2 positive cosine t. And that is part A. Part B is going to be starting at -2, 0, so that's over here, and we're going counterclockwise. So again, when I'm looking at these things, I'm going to first try to figure out which one is cosine. So if I'm starting over here, that's starting at the lowest possible x value. So that means x is a negative cosine, negative because it's starting at the minimum. Y is starting at 0 and it goes negative, so y is going to be a negative sine. And then that gives me my two equations, -2 cosine for the x and -2 sine for the y value. Next one, we're starting at 0, -2, so that's down here, and we're going clockwise. So again, just trying to figure out which one is going to be sine or cosine. So cosine is the one we start with, and that's going to be down here at a y value. I'm letting it be negative cosine because we're starting at a negative y value. X is going to go negative because we're going in a negative x direction. So x is going to be -2 sine t, and y will be -2 cosine t. Last but not least, we have starting at 2, 0, which I believe is over here, and we are going clockwise, so that way. Starting here, that means x is at a maximum, so x is going to be positive cosine, y is going here and going down, so it will be negative sine. So I'll have x equals +2 cosine t, y is going to equal -2 sine t. There you have it. That's 2, A, B, C, D. Did it really just jump to 5 and 6 next on my answer key? How messed up is that? Do you think I fixed that on the actual version? No idea. Let's switch to a new color. Alright, for what I have labeled as number 5, I have no idea. It's find the set of parametric equations for x + 1 squared plus y - 2 squared equals 4. So I recognize this as a circle, and it has a center point of -1, 2, and it has a radius of not 4, but 2. So that makes this pretty straightforward. I can just do x equals. They don't tell us a starting point. They don't tell us a speed, so we can just use our normal ones, which is x is cosine and y is sine. They didn't give us any sort of speed, so I can just put nothing inside of them, and then just need to have -1 for the x value, +2 for the y value, and we're always supposed to include some sort of interval. And there you go. That is what my answer key says is number 5. I have no idea if I fixed the numbering on your version or not. Oh. What my answer key says is number 6. We have x - 2 squared over 9 plus y + 5 squared over 25 equals 1. It's plus with both of them squared, so this is an ellipse, so it's going to be circular motion. We have a center of 2, -5. This is going to be the radius in the x direction, so 3, and the radius in the y direction is going to be 5. Again, they don't give us a speed or direction, so we just let x equal cosine and y equal sine. So that makes our life easy. So I have x equals 3 cosine t, and then +2, and y is going to equal 5 sine t - 5. Okay, the -5 and 2 coming from the center. Those are the radiuses. And then we have our interval. Boom, done. There we go. Now we start getting harder. And I get tired of sitting on the floor, apparently. He wants to come mount my whiteboard on the wall. What I have labeled as number 7. No idea if that's what it's actually called in your version. I should probably just look. Okay, circle with a center -2, 3, radius of 5, starting at 9 o'clock on the circle, so that's over here, and we're moving clockwise. The circle will trace itself one time in the interval from 0 to 8, so that's going to be our speed, okay? So we have 1 rev every 8 seconds, and I just need to convert this into radians per second. So I'm going to do 2 pi radians every 1 revolution, and that's going to end up giving me 2 pi over 8 or pi over 4 rads per second. And that's going to end up being the speed that we use. If I'm starting over here, that's going to help me figure out which one's cosine. So I'm starting at the leftmost x value, so x is going to be negative cosine, and we're going up, so y is going to be positive sine. So x will equal a -5 cosine, y is going to equal positive 5 sine. From here we'll put this inside, so pi over 4, and then t inside the parentheses, super important, must be inside, and then we get to the center, -2 plus 3, and then we have the interval that they gave us, which is from 0 to 8. So it wasn't so crazy bad, was it? Parametrization, an ellipse, fun. Center at 3, -4. We have a vertex. Ooh, crazy. Okay, fun. That tells us that what we used to refer to as A, or the major distance, is 5. Okay, and that's going in the x direction. So that's super important. This ends up being our radius in the x direction. They gave us a focus point. Ooh, now we're really getting tricky. A focus point of 6. So that's 3 away from the center point. We used to refer to that as the letter C. Okay, so that would equal 3. And in an ellipse, it was a squared minus b squared equals c squared. By the way, this is not going to be on the test, so don't. I mean, there really isn't any tests, but it's not on the test. So I get 25 minus b squared equals 9, and when I do all that work, I get that b has to equal 4. So that's important because this is actually going to be the radius in the y direction. Okay, so they didn't give us any sort of speed or direction, so we'll just let the normal stuff happen. So I have x equals 5 for its radius, cosine, no speed, so I'm just putting t. The center point was 3, so plus 3. Y is going to equal 4. I'll use sine, t, and then minus 4. So again, just to kind of emphasize the reason why I'm using cosine, sine, those are the normal ones we use if they don't tell us otherwise. And what that basically does is in this ellipse, wherever it is focused, we're starting here and we're traveling in that direction, which lines up with our unit circle, right? Our unit circle, we always start here and we move in that direction. So when x is cosine and y is sine, it connects back to what we are used to with our unit circle. And also just emphasize, you don't need to know how to do the conic section math like that. Oh boy, this one gets cray-cray. Holy cow. Alright, let's try to figure this out. Ferris wheel centered at 0.20. I'm going to put that here. I'm going to draw that. It has a radius of 20. Good, I drew it correctly. And it's going counterclockwise, so that's this way. Alright. And we have one rev every 12 seconds. Okay, so when I do the conversions, that's going to be 2 pi over 12 or pi over 6 radians per second for this first person. Now we have a second Ferris wheel centered at 15:15. This seems dangerous. with a radius of 15. Okay, so that's going to be like, oh boy, I don't know how to draw this. Like something like that, okay, where that is 15, 15. And this one is going counterclockwise, so that is going to be going this way. So they're rotating in the same direction. This one is 1 rev every 8 seconds. So it's going to end up, when we do all the conversions, as pi over 4 radians per second. And let's see, we got to write some equations, then we got to figure out the minimum distance. Ooh, we haven't done minimum distance in a while. All right, so I should continue to color code, huh? First one is going to be x equals, did they tell us where we start? Yes, we start at 3 o'clock for both of them. So that means we can use our traditional cosine and sine for x and y. So I got radius 20 cosine, radius 20 sine. I'm going to put the speed in, so pi over 6 t, pi over 6 t, inside the parentheses, can't emphasize that enough. If this is 0, 0, then we need to go up 20 in the y direction. So that's going to be the first person's equations. The second person's equations, they have a radius of 15. They're also getting on at 3 o'clock, so we can do the cosine, cosine, cosine and sine. Can't talk. Their speed is pi over 4. T inside the parentheses. And then I got to do plus 15 because their center point is 15, 15. So these are the equations, and what I'm going to do now is type them into the fancy calculator in function mode, right? So in our calculator, we, in theory, already have this written out, but we're doing, I can let this be y1, y2, y3, y4. This is going to be y5, and we should already have this formula typed in there if you didn't clear it for your sake. I hope you didn't. But I can basically do this, hit graph. When I hit graph and find the minimum after it takes 9 years to graph, I'm going to get a t-value of 1.64 and a minimum distance of 8.38. This is what we get at first, when we first look at it, if we don't do anything else. But if we continue looking at the graph, meaning we expand our time values, because we don't have any real time values here, we find later on that there's a time at 21.5 where the distance is actually much closer, 4.11. So this is not something that would pop up on a test where I would trick you like this, but if you actually continue to let this graph go, their distance basically goes like this, and there's the first point that we see at the 8.38, and then later on there's a 4.11 as the minimum distance. So it's just kind of a trick part that you have to look further in time to see if it happens to get shorter anywhere else. And then because these are circles, at some point it does start to repeat itself. So once you see in the pattern that it repeats itself, then you know that you don't need to keep looking. But again, that's probably not something that's going to pop up very often for you. Alright, this is what I have labeled as number 10. 60-foot Ferris wheel turning counterclockwise 1 revolution every 10 seconds. Ben stands at a point 80 feet to the left of the bottom of the Ferris wheel. At the instant someone's at 3 o'clock, throw the ball, and ooh, what a fun question. So we got someone throwing a ball, so that's a projectile, and then we have someone riding a Ferris wheel over here, which is going to be a circle. So if we deal with the circle person, they're starting at, where are they starting? Do they tell us? At the instant they're at 3 o'clock, they throw the ball. Okay, so time equals 0. That's where both of these models start off here. So that means for this one, we can just let x equal cosine, y equals sine. It's a radius of 60, so I'm going to have x equals 60 cosine, y equals 60 sine. It's 1 revolution every 12 seconds, so that means it's going to be 2 pi radians every 12 seconds, or pi over 6. And then, let's see, if we're starting way over here, we're starting 80 feet away, and it's starting up 60 feet. I believe that's what they told us. Ooh, man, this is a hard question. What a meanie I am for putting this one on. this guy over here, we got an initial velocity of 100 feet per second. We have a theta value of 70 degrees, and that's going to mess us up because this equation is in radians and this one is normally written in degrees. So what I'm going to do is just convert this into radians. So that's going to be 7 pi over 18 radians. So when I write this equation, it will be initial velocity 100 cosine 7 pi over 18. T is outside the parentheses this time, and y is going to be negative 16 t squared plus 100 sine 7 pi over 18 t outside the parentheses. And then we're just going to very carefully type this into the calculator to find the minimum distance to see whether or not this ball actually reaches the person on the Ferris wheel or not. So we do, that giant y1, y2, y3, y4 in function mode. This is y5, which has all of this lovely stuff already stored in there, hopefully for you. So we do all that in the calculator. We end up getting a t-value of 2.64 and a minimum distance of 17.65 feet. Boom, done. Again, make sure your calculator's in radians when we're doing this one. We're almost there, I think. Feel like circles stepped it up a little bit harder. Running on a track, I have this labeled as number 11. Running on a track, the track is 180 meters long and 100 meters wide, okay? So I have that as 180 going this way and 100 that way. It takes 75 seconds to run all the way around, all right? So that's one revolution every 75 seconds. So that's going to end up being 2 pi radians over 75 seconds. So that's going to be the speed that we're going to use. Let's write an equation. So we have x equals, so from the center of the circle, and I believe that we're starting right here because that's where that star is. So the radius in the x direction is 90, half of the 180. Cosine, because we're starting over there, 2 pi over 75 t, and y is going to equal 50, half of the vertical distance, 50 sine 2 pi over 75 t. That one wasn't so bad. Now we have someone else running. They take 85 seconds, so they're going to end up being 2 pi over 85 when we're doing this. And we're trying to write a set of parametric equations that's relative to the first person one, even though they're starting 10 seconds head start. So they're actually starting before them. So this is a great one for us to play around in the calculator to kind of see how it looks, but the first things all stay the same. Minus this, which is going to be 85 because it takes them 10 seconds longer. And this one's going to be 50 sine 2 pi 85. So this 10-second head start, remember we're doing it relative to this person. So when this t equals 0, we want this one, we want its t to equal 10, okay? So the way that we do that is we put another set of parentheses here and we just do t plus 10. So let's stop and think about that before we go too much further. If t equals 0 for this person's equations, then that's going to make this person have a t-value of 10, which gives them the 10-second head start. So we just do, in parentheses, t plus 10. And that gives us that one. We want to figure out what are the position of this person right here at t equals 0. So I'm just going to basically model that. So I'm doing x of 0 and y of 0 in the calculator, and you should get 66.51 and 33.68. And there you have it. So tricky one about this one is going to be how to handle that 10-second head start, but it's not too crazy once you kind of get the hang of that. Oh my goodness, this is the last one. So exciting. Number 12. We got more people running. Why are so many people running? My goodness. They're going at 5 revs per 9 minutes clockwise. So that's really important. And it says that they're starting at the bottom. I'm trying to look to see where it is. Yes, starting at the bottom, going clockwise. So when we write this person's equations, this is the first thing I want to deal with. And I want to turn it into seconds, okay? So to do that, I'm going to have 5 revs per 9 minutes is going to be times 1 minute every 60 seconds, and then times 2 pi radians every 1 revolution. And when you do all that fancy math, we should get something like pi over 54 radians per second. And what that actually tells us is how fast they're running in seconds, right? So if I didn't reduce this, this one would have been 2 pi over 108. So that means it takes them 108 seconds to run around this track. So when will they reach the location on the track that's closest to the person stretching? Okay, so we got all this stuff here. We started here. There's a person stretching right here. The closest distance is going to be this part right here. So I need to figure out when are they right there. And we can actually use this information over here. This is the halfway point from where they started. So I know the answer to part A, without really doing a whole lot of fancy math here, is going to end up being at t equals 54. And I know that that distance, if this is 100 and the radius is 300, then I know the distance is going to be 200. We can also plug this in to the equation in function mode if you're not positive by writing the equations here. So the equations for this first person is going to be, let's see, starting down here, that's going to be a negative cosine. So radius negative 300 cosine, and then negative x value for the sine as well. We got our pi over 54 as the speed, pi over 54. And we can assume the center is 0, 0. So these are our equations. So I can plug this and then also plug this point in as the actual thing in the minimum distance, and it would give us the same exact value, or we can just kind of use our knowledge that that's going to be the shortest distance. We want to know where they're located, so I'm just going to basically do x of 40 and y of 40 to get those points. So that's going to be negative 218.21 and 205.87, I believe. And the last one is tricky, right? We want to figure out how far has she actually traveled in the first 40 seconds. So this is fun. It takes her 108 to run the whole thing. So right now she's at 40 out of 108, and we're just going to multiply that by the circumference. So this gives us the percent that she's run so far times the circumference. That's going to be 698.13 feet. And that's how far she's run. Boom, there we go. I think that's all said and done. Woo!